Hello, welcome to week 3, day 1 of Lab 1102. Uh, Wanted to get some administrative things out of the way first. First off, you can turn things in late with no loss of points. We've got enough going on right now. I'm not that concerned about you needing an extra day to do something. Um, Honestly, the same goes for the discussion activities for attendance. I will mark you as late, but um, you will switch from being an unexcused absence to being late instead of being absent. Um, that's all. All right, let's move on to talk about what we're learning today, which is largely vocabulary stuff. A lot of these are words that are slightly different words for different words for very similar concepts. Um, so let's start with the first one. First off, and this is the one on this page that's not a similar concept to the rest. Um, Analyte is the word for what we're wanting to measure or learn about. So, for example, if we were wanting to measure the sodium content in a saltwater solution, sodium would be our analyte. Right? An analysis is the process of trying to learn about the analyte. Measurement is finding the value of a property. So, for example, measuring the measuring the volume and measuring the mass. You're finding out values of those properties. Measuring the absorbance of light at a certain wavelength, you're finding the value of a property. You're measuring something. Determination is the output of an analysis or analyses. Analysis is the plural of analysis. It looks like a misspelling. Um, so to kind of put those in context, if you want to use them all in a sentence that shows the differences, in this analysis we measured the mass and volume of our saltwater solution and determined that well, sorry, I'm trying to tie it into my earlier examples and that's failing. So in this analysis, we measured this, and this, and determined that the analyte concentration was whatever it is. Okay, so some more words with slightly subtle differences. So a sample is the thing we're measuring. So if I take some salt water, that's my sample. I've got a sample of salt water. Um, the matrix is the stuff that's in the sample. So in this case, my saltwater matrix, it might be, you know, sodium sodium chloride and water. If it's seawater, it's probably got other minerals in that as well. But that that is my matrix. So if I'm measuring THC levels in blood, for example, blood is my matrix. Sometimes it's specific to the stuff in the sample that's not the analyte. Sometimes it includes that. It's kind of context dependent. The blood chemistry one, for example, blood is the matrix. In the saltwater one, the sodium that is part of the analyte that's our analyte is also included in the matrix. Um, I think it has to do with how major a component it is. All right, so there's some more subtle differences, similar concepts, subtle differences. A technique is the principle used to study something in very broad terms. So the only example for this I could really think of easily was honestly kind of silly. So stroking a companion animal, so petting a dog, petting a cat, those would be broad broad examples of stroking a companion animal. So method is the specific application of a technique. So for example, giving a dog a belly rub, scratching a cat behind the ears, specific applications. Procedure are the directions. So for example, stroke the cat in the direction of the fur, like, If you've ever been around a toddler, they sometimes want to pet the cat backwards or pet the dog backwards, and that's no fun for the animal. For cats, it might be no more than 3 times, and then they're going to bite you. Finally, so we've gone from general techniques, rather general methods, a little more specific. Procedure is, you know, even more specific and broken out into some level of detail. Protocol is the final level of specificity, of detail. Uh, it's generally strict, formal, something that's required by law for some reason. So your EPA standard methods are protocols. This will be done this way. If I were to take the cat petting procedure more formally, I would probably specify the pressure to apply as you're stroking the cat, the length of the stroke, um, things like that. It would be very, very laid out and formal. Frequently, those are a legal requirement to follow for some reason. All right. So, in terms of techniques, so back to that top level, very broad, we can classify techniques into 2 broad categories. Um, you can The technique can measure something relative to the total amount of a sample. This is called a total analysis or classical techniques. So if you think back to the first or second day of class where we looked at an example of measuring nickel content in ore, uh, you'd have your sample, you'd do something with it, some of it would settle out, you would measure that amount that settled out. That amount would be changing depending on how large your sample was. So um, things like mass, you're measuring the total mass of something, you're measuring the total volume of something. So these are all based on the total amount of the sample. Um, you've also got the other possibility is things that are relative to the analyte concentration. These are sometimes called instrumental techniques. So uh, things like concentration itself, resistivity, absorption at a certain wavelength, something that changes depending on how much of the analyte there is. So, for example, resistivity, if you've got ultra pure water, has a very high resistivity. No matter how much ultra pure water you have, that resistivity doesn't change. It changes with the salt concentration in the water, um, not just sodium chloride type salt, but broadly um, ion. I get ion concentration in the water. Same thing with absorption at certain wavelengths. So that changes with the concentration of whatever's absorbing light at that wavelength. The book will go into quite a bit of detail with the math here. The important thing to remember on this math is this S here is the signal. So it's the intensity of the signal. It's your resistivity measurement. It's your mass measurement. It's the output of it's your measurement. So your measurement is proportional either to the total amount of something or the concentration. And then this is just a proportionality constant. So, and frequently we will try and be working hard to make sure we're doing this in a range where where this relationship is linear, so that this k is just a number. It's not some equation. Um, so, for example, there's a law in chemistry called Beer's law. It's quite popular with undergrads, but all it says is that the absorption of light at some wavelength is a constant times the concentration, and that constant is the Beer's law coefficient. That's all that Beer's law is. An example of this, I suppose we could put density in here and have either mass or volume, one or the other, there as an example of how that might work as an equation. I can't think of another off the top of my head. So, all right, so let's talk about criteria for selecting one test method over another. First things we have, concepts we have related to that are accuracy and precision. So accuracy, as you can see in the thing, is how close something is to the target. So you can see our grouping. If we averaged that out, it would be on target. Precision is the size of the group. So you can see that's a big group. It's not very precise. This is a small group, so it's precise, but it's quite a ways away from our target here, so it's not accurate. Again, on this side, we've got, this is neither accurate or precise. It's a large group and it's well off. This is both accurate and precise. It's a small group that's centered on our target. Other things that are along those lines, we have sensitivity. So that's the smallest change we can measure. So if you think back to graduated cylinders, that line distance in between lines, those lines indicate, we can kind of estimate in between the lines, but that estimate of, halfway in between the lines or over halfway in between the lines is as small as we can measure. The detection limit is not the smallest change we can measure, it's the smallest amount we can measure. So again, if we think about that graduated cylinder, there's some gap between the bottom of the cylinder and where our measurement line starts. We can't measure in that gap, so that lowest line is our detection limit. It's the smallest amount we can measure. So now next we have specificity. So that is the degree to which the signal only depends on the analyte. So if we look back to this equation here, we think about this. It's possible that that our signal here is equal to, a coefficient times the concentration of our analyte, plus maybe a coefficient, another coefficient times the concentration of something else, plus another coefficient times the concentration of something else. There could be multiple things it could also depend on. So the extent to which it depends only on our analyte is how specific the test is. So an example of something that's not specific, depending on what you're trying to use it for, might be pH. It will tell me how much hydrogen ion, the amount of hydrogen ions in the solution. It is specific to hydrogen ions. It is not going to tell me how much of those hydrogen ions came from the sulfuric acid I put in versus how much came from carbonic acid that it, is something that you get from CO2 in air, or how much came from the nitric acid I might have put in. It's going to tell me the total pH, not the hydrogen ions from each source. So an interferent is those other things besides the analyte that might contribute to the signal. So if I'm trying to determine hydrogen content from sulfuric acid, the interference would be the nitric acid and the carbonic acid, for example. Selectivity is, related. It's a measure of freedom from interference. Okay, so it's our final selection criteria slide. A test can be robust, which means it is relatively free of interference and works in multiple matrices. So, for example, we might need to have different tests for testing for something in blood solution versus in water. So if we had a test that worked in both, it would be more robust than a test that only worked in one or the other. A test is rugged if it's relatively immune to environmental conditions. So if I don't need to be in a strictly climate controlled lab to run this test, it's more rugged. If if I have to be in a 20 C room with 50% relative humidity or my results won't be valid, then that test is not rugged. Um, so the scale, of course, is how large a sample is needed. If I have to use very large samples to get results, I might well be better off trying to find something that trying to find a different test that can use a smaller sample. Uh, you know, especially in a production environment, a sample represents material that I can't make and sell. So in a cannabis lab, the larger sample you have to have, the less product you have going out the door. In a blood testing type environment, the larger sample you need, the more blood you have to draw from somebody. Equipment, a lot of times there's a trade-off between very expensive equipment that will work with a smaller sample in less time versus and frequently less expensive chemicals maybe versus something that's going to take use very cheap equipment, uh, but might be something that takes 56 hours, but it will be very cheap to set up. Just time. Uh, Time, you've got to think about how long it takes to prepare the sample and do the measurement. Um, so back to equipment, some of the equipment that might be faster or more necessary. Sometimes the measurement time, even with that, can take quite a while. So depending on what you're measuring, you might need 6 hours for the sample to go through the gas chromatograph, and then you can get another sample through, and so they can still be very time consuming. Um, Sometimes you can adjust that time as a trade-off with selectivity or sensitivity or detection limits, depending on what you're trying to do. There's some trade-offs there around time. You need to remember the sample preparation. Some methods you've got to dry the sample, which can take quite a while. Then it needs to be if you're measuring metals content in a plant material, for example, you're going to need to dry it. You're going to need to digest the sample in nitric acid. So you've got 8 to 12 hours to dry it probably. Maybe a little less, but likely you're going to pop it in and walk away for hours, possibly overnight. 20-30 minutes to cook it in nitric acid and boil it down to very concentrated solution. Then you're going to need to dissolve it and let it come to about room temperature. All that before you can actually run the measurement itself. Final thing to consider is the cost. So you've got consumables, reagents. So is this going to, pipette tip is an example of a consumable. You use it once, you throw it away. Some tests have for example, chemical oxygen demand and biological oxygen demand tests for wastewater are typically a little test tube you buy. You put your sample in. It's got the reagents in it. You put it inside the instrument that reads it. Then you throw that away, and you're done with it. So that's a consumable. Reagents are any chemicals you need to use to do the measurement. So in the metals content in plant material, for example, you need nitric acid as a reagent. You're going to need pure water as a reagent. You're going to need a sample of the metals that you're trying to measure as a reagent to set up standards with. All of those go into how much it costs to run each sample. If you're, depending on what instrument you're using, you might need some compressed gases. Um, might be helium, might be hydrogen, might be an oxygen, nitrogen. It varies depending on what you're doing. Okay, so those are some of the concepts and vocabulary you'll need as you're proceeding in your career in this. That's all I have for the lecture part today. Um, in the in-class portion of the lecture, the online part, we'll go over homework that was due today and spend some more time on that and on the calculations and practicing that. And I hope to see most of you then. Thank you.